So we have discussed so far measurement error, ideas about measurement error, and let me just uh, 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 maybe give you a little more insight into um, what are measurement errors and what kind of measurement errors exist. So there are two kinds of measurement errors. One is called as the random measurement error and the other one is called as a systematic random error, right? Now the idea of measurement error is these two measurement errors is very simple. The random measurement error tells that there is no specific pattern, there is no definite pattern of this measurement error. So for example, if I were to ask you this question, let us say the question is my being an academic or in an academic profession, even for PhD students. So I'm treating you also in as an academic profession. Being an academic is a serendipity, right? So this is a question that I ask you on a scale of 1 to 5, strongly disagree to strongly agree, right? Now, the you can think about it, write your answer on a piece of paper. Okay, my being an academic, don't Google the meaning of serendipity. Without Googling up or looking up the meaning of serendipity, if you were to write what is your answer, you will get different respondents will give different responses. Now the question, because what has happened is you wanted to test, maybe your construct was uh, academic interest. Okay, why do people take academic as a profession? Okay, let us say there is some construct called as interest in academics, but what you ended up doing was you have ended up also testing the English proficiency, right? So I told you that errors happen, one, because we don't know the true construct. So we are not sure whether what we are measuring is right or not. And the second is there are problems with items. Okay, the items that we have written, which may also create a lot of another kind of confounding that can happen. So, well, people who will understand what serendipity is, they will respond to the item in a particular manner. People who don't know what serendipity is, well, they will make a guess and they will respond on the item. So there will be randomness. Okay, there is going to be randomness, and this kind of an error is called as an idiosyncratic random error because it is idiosyncratically distributed as per your proficiency of English, right? Now, another question is, let's say I like eating vegetables as I believe in in God. Again, now this is a second question on a scale of 1 to 5, strongly disagree to strongly agree. Now, there is no hard English here. There is no difficult English. I like eating vegetables as I believe in in God. Now, no difficult English, but what has happened is you have mixed two questions. I like eating vegetables, that is one part, and I believe in God. I like eating vegetables, okay, but what is it got to do with my believing in God? Okay, so what will happen is this is another kind of a problem that will confuse everybody who is going to respond. Some will say, yes, I believe in God, but I don't eat vegetables. I believe in God and I eat vegetables. I eat vegetables, but I don't believe in God, right? So there can be all kinds of combinations that can come up, which can again introduce randomness in your data. And this is called as a generic random error. This will be across the population. And this kind of question in survey design is called as a double-barreled question. When you have two questions and you ask them in one go. Okay, so this is another kind of problem that may crop up. So this which will lead to random measurement error. Now the characteristic of random measurement error is if you see if you have two series, let's say you had two items X and Y, okay, and you had some responses, okay, whatever, 3, 2, 1, and there is now some random error that has got into this, that has confounded these responses. Then what will happen is that it will always reduce your it will always reduce your correlation because of the uh, randomness. So remember, whenever there is any randomness, correlation between two pure random numbers, random number 1 and random number 2, correlation between two pure random numbers is always 0. Okay, random numbers are not correlated to each other. So if you introduce randomness, if there is randomness in your measure, the correlation will always be attenuated between X and Y. Okay, it will always be reduced uh, as compared to what the original correlation was. So that is one characteristic of random error. There is another kind of a random of measurement error which we call as systematic measurement error. So one is random measurement error, another one is systematic measurement error. Now what happens with systematic measurement errors? Systematic measurement errors are errors that have a definite pattern in a particular direction. Definite pattern. So for example, if I were to ask this question, I am a motivated student to all of you on a scale of 1 to 5. Okay, strongly disagree to strongly agree. I am a motivated student. What do you think the responses of people most likely will be? They will be 3 and above, right? 3, 4, and 5. Most of the people will show a definite pattern of response will be which will be 3 and above. So there is now a systematic pattern that we can observe in this. This is actually called as social desirability in survey design. Social desirability problem. social desirability. So now you have introduced, because of the way you have developed your measure, there is a social desirability that has been introduced. So what happens, or what is the outcome of systematic measurement error? Systematic measurement errors can actually have two things. First, they can let the correlation unchanged, and second, they may reduce or increase the correlations. Okay, so let me just show it to you. Let me just, yes, so it will be definitely, social desirability will be a problem with your reflective constructs. Actually, all of this that I am writing here is in the context of reflective indicators. So it will be happening even in your in reflective uh, constructs, definitely. So let me just explain this part, and then I will take your other questions. Now let us say, I hope you can see this. Okay, let us say there was one series, one set of numbers. So these were two items, X, item Y, two items of a construct. This was the response of people on X. This was the response on Y. I have just taken, this was the true response without any error, without any systematic error. So the correlation between, I have computed the correlation, comes out to be 0.1. I have used this formula, correl. Okay, this is the correlation. Okay, so this was the true correlation between X and Y. Now let us look at what happens if there is a systematic bias of +1. So 5 becomes 6, 4 becomes 5, 5 becomes 6 again, 3 becomes 4, 4 becomes 5, 5 becomes 6, 1 becomes 2, 2 becomes 3, 5 becomes 6 again, and 3 becomes 4. And for Y, there is a systematic bias of, let's say, -1. -1. So for some reason, there is a systematic bias. So 4 becomes 3, 5 becomes 4, 3 becomes 2, 4 becomes 5. Sorry, 5 becomes 4, 4 becomes 3, 2 becomes 1, 3 becomes 2, 3 becomes 2, 4 becomes 3. Now you see there is a systematic bias of +1 in X, systematic bias of -1 in Y. But you look at what happens to correlation between these two series, it remains absolutely unchanged. So this was 1.0.10881. This is also 0.10881. So there is no impact on the correlation between these two series. Now let us look at another one. This is again a systematic bias of +1, but it is captured on a Likert scale, which is of 5 points. Okay, so it is a 5-point Likert scale. So you cannot have a 6 on a 5-point Likert scale. Okay, so what you have is 6 has to be truncated at 5, because that's the maximum on a 5-point Likert scale. 5 remains 5, 6 again has to be truncated at 5. Okay, 4 is okay, no problems there. 5 is okay. 6 again has to be truncated at 5. 2 is fine. 3 is fine. 6 has to be truncated at 5 and 4. And then this again is measured on a 5-point Likert scale. So 4 becomes, 4 becomes 3, 5 becomes 4, 3 becomes 2, 5 becomes 4, 4 becomes 3, 2 becomes 1, 3 becomes 2, 3 becomes 2, 4 becomes 3, and 2 becomes 1. Okay, so this is again minus 1. So this the same series that is here is also here. Now look at what has happened to the correlation. Correlation, my friends, has actually gone up even though there is a systematic bias, right? So what is the message that we can take away? So one, I told you that systematic error may be there, but you may still get the same correlation. Systematic error may be there and you may get a even higher correlation between your items. So what is the message here? The message is that when you are looking at your data sets, you cannot identify systematic errors using statistical techniques, because systematic errors can be additive, that means no change in correlation, and correlational kind, that means you can, the systematic errors will change correlations positive on the higher side as well as also on the lower side. That means what? You cannot capture whether there is a systematic error or not by looking at the correlations between the items. And most of our statistical techniques are based on correlations. So the idea is, whatever we are, why I am telling you, this is all the things that we are going to do: reliability testing, factor analysis, structural equation modeling in this workshop. It is going to be directed towards random error. Okay, random errors, because for sure random errors attenuate relationship, right? This is an important artifact of random error. So you can easily capture. If you have to capture systematic errors, then you cannot capture it through analysis. Okay, you can try to, there are techniques, again, we'll talk about common method testing later on, but you will have to tackle it using by changing the way of collecting your data. So you will have to change the items that you write. You will have to change the way you collect data. So you may need to collect data from some other source. Okay, you may need to collect data from peers, from supervisors. You may need to break down the data collection over a period of time, and so on. So the research design has to change in order to capture uh, the kind of uh, systematic bias that can come up in our measures, right? So this can be another reason why there is always a tendency of measurement errors to be there in our measures. So we come back to the same diagram concept, which is the dotted line, the solid line, which is the operationalized construct, that means the measure, And what this right side picture is showing, the greater the abstractness of the construct. Okay, so you see length and measurement of length. There is not much of a difference. Weight and measurement of weight. But the moment you talk about preference, perceptions, attitudes, the measurement errors are larger when we talk about attitudinal behavioral measures. This diagram shows, this is again from, these diagrams are from the reading, what is measurement, that is there in the readings folder. This diagram shows that for one construct, there can be multiple equivalent measures that are possible, because again, since the gold standard is unknown, different people may come up and devise different kind of measures for the construct, right? So there are multiple things. This one again shows preference for numerical information. You can make it more specific. So consumers preference, employees preference, or general preference for numerical information. So this you can make it more abstract by showing that it is. So preference for numerical information will have two subdimensions. Okay. This is again different ways of conceptualizing. And the more general you make it, the more abstract it becomes, right? So you see the level is going up and its measure is going to be different, right? So preference for numerical information will have consumer's preference, which in turn could have another kind of dimension. So one construct nested under another, and this construct of our interest, preference for numerical information, will become more and more abstract as we make it more general, applicable to wider. And the more generic it is, the more abstract it is, the harder it is to capture it, and the greater is going to be the possibility or probability of the measure being confounded by errors of measure.